In this video, we'll take a non-homogeneous system and solve it all three ways: diagonalization, undetermined coefficients, and variation parameters. So yes, this will be long, but it will cover all three options for approaching this problem. So in every case, the first step is always to look for the eigenvalues of the coefficient matrix for this system. So our determinant of A minus lambda I is going to be minus 6 minus lambda, 4 minus lambda plus 16, the lambda squared plus 6 lambda minus 4 lambda minus 24 plus 16, lambda squared plus 2 lambda minus 8, which is lambda plus 4, lambda minus 2. I have eigenvalues at -4 and +2. Now I want to find the eigenvectors. Lambda equals -4. We are adding 4 on the diagonal, so we'll get -2 minus 8 to 8, which reduces to 1, 4, 0, 0. So an eigenvector here is going to be 4 and -1. And for lambda equals 2, we're subtracting 2 off the diagonal, which makes the matrix -8, -8, 2, 2, which reduces to 1, 1, 0, 0. So a vector here is 1, -1, which means the general solution to the homogeneous problem is C1 times 4 minus 1 e to the minus 4t plus C2 1 minus 1 e to the 2t. With this now set, we can go into each of our three different methods for solving the non-homogeneous part of the problem, because we need this basic information for all of them. Method 1 is diagonalization. So with diagonalization, we can look back at our solution and use that to build the matrix P, which is the eigenvectors in a matrix, and D, the eigenvalues in the same order. We can also now compute P inverse, which is 1 over the determinant, flip the diagonal entries, negate the off diagonals. This will be a -1/3 in front. So P inverse is going to be 1/3, 1/3, -1/3, and 4/3. Minus sign on that 4/3 there. With all this, we can now go about solving our problem. So we know that if we define x as p times y, then y will solve y prime equals dy plus P inverse of f. We know what dy looks like because d is diagonal, but for P inverse f, we have to compute that out. Pulling in our f function, which is the non-homogeneous part of the original equation, which is t plus 1 and 3, gives the vector here as t over 3 plus 1/3 plus 1, negative t over 3 minus 1/3 minus 4, or t over 3 plus 4/3 minus t over 3 minus 13/3. Thus we have that our reduced system in terms of y's will be that y prime equals -4, 0, 0, 2 times y plus that vector. Thus we can now split this into two decoupled equations and solve them separately. We have y1 prime equals -4y1 plus the first component of that vector, and y2 prime equals 2y2 plus the second component. So we'll move the term to the other side. 1 prime plus 4y1 equals t over 3 plus 4/3. The integrating factor that I want here is e to the 4t. The left side then becomes e to the 4t y1 prime is t over 3 times e to the 4t plus 4/3 times e to the 4t. We'll have to integrate both sides here, and this first step here is going to require integration by parts. So at e to the 4t times y1 equals, the first step we're picking u to be t over 3, dv is e to the 4t, so I'll get a t over 12 e to the 4t minus an integral of 1/12 e to the 4t, and then just plus a 1/3 e to the 4t plus c1. do the last integral out. And since 1/3 is 16 over 48, I can multiply through by e to the 4t and get that y1 should equal t over 12 plus a 15 over 48, which is our constant term, and plus a c1 e to the minus 4t. Now we can solve the second problem in exactly the same way. We'll move the 2 to the other side. Minus 2y2 is negative t over 3 minus 13 over 3. The integrating factor that I want here is e to the minus 2t. So this side becomes e to the minus 2t y2 prime equals minus t over 3 e to the minus 2t minus 13 over 3 e to the minus 2t. We need more integration by parts here, and because there's minus, I'm going to be a little more careful, work this one out in more detail. The integral of t over 3 e to the minus 2t, we've got our u as t over 3, our du is 1/3, dv is e to the minus 2t, so v is negative 1/2 e to the minus 2t. And so this becomes a negative t over 6 e to the minus 2t. And then plus, because there is a minus sign on the integration by parts and a minus sign on the v term, integral of 1/6 e to the minus 2t, which then that will integrate to a minus 1/12 e to the minus 2t. Great. So then our expression here, e to the minus 2t y2 after integrating both sides, will give me a positive t over 6 e to the minus 2t because I'm canceling out the negative sign that is here. Then plus 1/12 e to the minus 2t, and then plus 13 over 6 e to the minus 2t. So for y2, we get, after multiplying through by e to the minus 2t and not forgetting the plus c2 over here, we get a t over 6. 13 over 6 is 26 over 12, so plus 27 over 12, and then plus a c2 e to the minus 2t. So we've got our two different y functions. We can now stack them into a vector to get our solution y. Great. But we are not done yet, as that is just our intermediate solution y. We have to build that back to get to x, because x is defined as p times y, and p, as I mentioned from before, is 4, 1, minus 1, minus 1, then times this vector y, and then we can just carry this multiplication to get our solution x. Now I want to combine these terms together, make it look a little bit nicer. So x is t over 3 plus t over 6 is t over 2. 15 over 12 plus 27 over 12 is going to be 42 over 12, which is 7/2. And then our 4c1 e to the minus 4t, and our c2 e to the 2t. And on the bottom, we have negative t over 12 minus t over 6, which is minus t over 4, because that's 1/12 and 2/12 is 3/12 is 1/4. 57 over 48 simplifies to 5 over 16. 27 over 12 simplifies to 9 over 4. And our other two terms stay. The c2 e to the minus 2t. 9 over 4 is 36 over 16, meaning this here is a negative 41 over 16. And we can then split this up in different terms based on the function t that's attached to make it look at something we will see with our other methods as well, giving us the following. So we have our t terms here, 1/2 and minus 1/4. We have our constant terms, 7/2 and minus 41 over 16. And our homogeneous part here, again, the homogeneous part showing up is not surprising because that is how all these solutions work. There's a non-homogeneous part plus a part that solves the homogeneous equation. So there is the diagonalization approach. Method 2, undetermined coefficients. So based on our non-homogeneous part, which was t plus 1 and 3, our guess should be a t plus b, but now these are vectors. So we'll have a1, a2 times t plus b1, b2. And now we need to plug this into both sides of the equation. So for the derivative, that one's easy. This is just a1, a2. Because the t goes to 1 and the constant term goes to 0. For the other side, we have the matrix, minus 6, minus 8, 2, 4, times x plus our t plus 1 and 3. When we multiply that by our guess for the solution, we're going to apply this matrix to these vectors and leave the t functions alone. So we'll see minus 6a1 minus 8a2, 2a1 plus 4a2 times t plus minus 6b1 minus 8b2, 2b1 plus 4b2 times constant, and then plus t plus 1 and 3. And then we just want to group these terms into where they belong. So this t will result in a plus 1 being here. This 1 will be a plus 1 here. And this 3 is a plus 3 down here. Now we got to pair up our equations. For the t's, there's no matching t on this side of the equation, so those are both going to be equal to 0. So I'll get two equations from this term right here that say minus 6a1 minus 8a2 plus 1 equals 0, and 2a1 plus 4a2 equals 0. And then for the 2 over here, I have to pair them with the a1 and a2 here. So minus 6b1 minus 8b2 plus 1 equals a1, and 2b1 plus 4b2 plus 3 equals a2. Great, let's start by solving the a equations because they are by themselves, then we'll use the solution from the a's to plug into the b's. So from the a's, I can rearrange the second equation to tell me that 2a1 equals minus 4a2, or a1 is minus 2a2. I will plug that up into here to tell me that minus 6 times minus 2a2 minus 8a2 plus 1 equals 0. 12a2 minus 8a2 equals negative 1. 4a2 equals minus 1, or a2 is minus 1/4, which coming back up here tells us that a1 is 1/2. Those numbers should look familiar. Then we can jump over to the b equations with our newfound information for a1 and a2. So those equations will now tell us that minus 6b1 minus 8b2 equals a1, which is 1/2 minus 1, and 2b1 plus 4b2 equals a2 minus 1/4 minus 3. We can simplify this a little bit by combining these fractions. This is minus 1/2, and this is 13 over 4. I'm then going to double the second equation, be able to cancel things out, to leave me with minus 6b1 minus 8b2 equals negative 1/2, and 4b1 plus 8b2 equals negative 13/2, and then add these together. I will get that minus 2b1 plus 0b2 is negative 14 over 2, or minus 7, so b1 is 7/2. And then from that, we can conclude that since 2b1 plus 4b2 equals negative 13 over 4, this 2b1 is just 7. So 4b2 equals negative 13 over 4 minus 7, which is 28 over 4. That's a 41 over 4, so b2 is a negative 41 over 16, which now lets us write out our entire answer. So our answer for this version is x of t is a, which was 1/2 and minus 1/4 times t, plus b, 7/2 and negative 41 over 16 times constant, plus our homogeneous solution of c1, 4 minus 1, e to the minus 4t, plus c2, 1 minus 1, e to the 2t. Finally, we have method 3, variation of parameters. So for this, we want to build our fundamental matrix, x of t, which involves a general solution. So our solution before, we scroll up to see what we had for undetermined coefficients. We have the 4 minus 1, e to the minus 4t, and the 1 minus 1, e to the 2t. So that becomes this matrix here, 4 e to the minus 4t, minus e to the minus 4t, e to the 2t, and minus e to the 2t. I will need this inverse to work this out. So this inverse is 1 over the determinant, and then times swapping the diagonal entries, and then putting a negative sign on the off-diagonal ones. Now this expression here is a minus 4 e to the minus 2t on the bottom, plus e to the minus 2t. So it's going to be a negative 1/3 e to the 2t because it's a minus 2t on the bottom. So pushing that through the entire matrix gives the actual inverse here is a 1/3 e to the 4t a 1/3 e to the 4t, a minus 1/3 e to the minus 2t, negative 4/3 e to the minus 2t. Now that we have this x inverse, we can now go about the variation of parameters approach, which is that our u prime should be x inverse times f. X inverse is that matrix we just wrote down. F is our function at the start of the problem, which is the right-hand side, or the non-homogeneous part, is t plus 1 and 3. And then we can carry this multiplication to get our u prime. Or, combining them to make it look a little nicer, u prime will be t over 3 e to the 4t plus 4/3 e to the 4t and negative t over 3 e to the minus 2t minus 13 over 3 e to the minus 2t. Now, if those functions look familiar, you should not be surprised. They are actually similar to something we've seen before, because in solving the problem 3 different ways, these functions are the exact same as the ones that we had in diagonalization. They are exactly the two functions that we see here and here in the diagonalization process. And this is not surprising because we're solving the same exact problem multiple ways, and 2 of those ways, namely diagonalization and variation parameters, both involve integrals. The fact that the same integrals of the same function show up in the process is not really surprising. So I'm going to cheat here a little bit and use the fact that I already know what these integrals and derivatives are in order to just get to the answer for the next part here. If you're going to solve the problem just by variation of parameters, you would just do these integrals that we did right here at that part of the problem. So we can just copy the integrals that we have here down to that part to get our answers. We will get that our function u here should be the following. And then finally, we get our solution as x times u. Our solution x here should be our fundamental matrix x times this u. Matrix x, we had way before, 4 e to the minus 4t and minus e to the minus 4t, e to the 2t and minus e to the 2t, times this vector u. And we can carry this multiplication to get our solution. And if we collect terms and collect expressions just like in the last couple examples, we will see that we get our solution x as 1/2 minus 1/4 times t plus 15 over 12 plus 27 is 42 is again 7/2, and we'll see the negative 41 over 16 down here, plus a c1 4 minus 1 e to the minus 4t, a c2 1 minus 1 e to the 2t. So there's this problem also worked up by variation of parameters, and if we check, there's our variation of parameters answer. We have our undetermined coefficients answer, and our answer from diagonalization. And all of these match, they are all the same, they will all get you to the same answer for these problems. It just depends which method you want to use, which one you feel better about for a given problem. They will all work. Diagonalization works best for real and distinct eigenvalues. Undetermined coefficients works if you're happy figuring out the right guess to make for the right-hand side of the equation, for the non-homogeneous part of the equation. And variation parameters works every time. You just need this fundamental matrix to build from in order to find the solution. Which one you want to use is up to you, but all of them work out for solving these non-homogeneous systems of differential equations.